Okay, so as I said I ended the last video, I was talking to you about polar molecules. And I was giving you some examples that you can see on the screen here about how a molecule can be polar or nonpolar. And this is based on how the elements connected to that central atom arrange themselves. And from that, we can see if a symmetry of charge results or an asymmetry of charge results. And so in the center here, I have the CCl4 molecule. The 4 Cl's are bound to the C. They've spread out into a tetrahedron. They are all pulling on electrons equally. They cancel each other out. This is nonpolar. If I replace one of those Cl's, or if I replace those Cl's with H's except for one, now I only have one chlorine pulling with much force on those electrons, and that creates an asymmetry in the charge distribution. Again, whenever I have a lone pair on the central atom, I will create asymmetry. And so what I wanted to do before we go on and talk more about polarity is go back to this chart here, which is the shapes, because the shapes can be really valuable in telling you if something's polar or nonpolar. If you have a linear shape over here, and actually, you know something, let's go back down, and I'm just going to quickly insert a page, or I'm going to do it right here. Just to insert a page, show you what this looks like. Actually, yeah, I'm going to insert a page below this so that we're consistent. So I'll go right here. We'll insert a page right there below this. So let's add a page, and then we could put it right there. So if I have a shape that is linear, it depends on what's connected to the central atom. Because what I could do is I could connect two of the same elements like we saw with CO2. Now each of these O's will be pulling on electrons in opposite directions, like two people pulling on somebody's arms in opposite directions, and they'll cancel each other out, like a tug-of-war where both teams are equally matched. But imagine if I had a tug-of-war and I had, you know, HCN like this. Well, now when I look at the electronegativities, I see that C is pulling more than H, and N is pulling more than C. And what ends up happening is you get this negative part of the molecule versus a positive part of the molecule. And because of that, you have two situations for linear. You could be nonpolar, or you could be polar. Now remember, in the other video I said, well, if you have a lone pair, so if we have, bent, and that could be like this. That could be where you have, that could be where you have SO2 like this with one lone pair. Or it could be where you have H2O, where you have two lone pairs. But what ends up happening is this bent shape, what it ends up doing is it ends up causing asymmetry. And so whenever you're bent, you are always polar. Same thing if you're trigonal-pyramidal. If you're trigonal-pyramidal, then you'd have a situation where you would have, like NF3. Because of the pyramid shape of this and this lone pair forcing these F's into that position, you're always going to be polar. So whether you're bent or pyramidal, you're always polar, the molecule. Now, what if you have something where there's no lone pairs? So we did linear, and we see the same trend. With linear, we could be polar or nonpolar. Well, if we're trigonal planar, that flat plane, well, we could do the same thing we did with the linear one. We could make a nonpolar molecule like this, or we could take one of those F's off and put H's there and leave one of the F's alone. And so now you can see on the left we have a polar molecule, on the right we have a nonpolar. On the left we have a nonpolar molecule, and where we have the H's and the F we have a polar molecule. It's very clear on the left there's that symmetry, on the right there's that asymmetry of charge. And we saw with CH or CCl4 versus CH3Cl, how changing those atoms around it changes the pull that those elements are pulling on the electrons. And that will result in a situation where you'll either be nonpolar or asymmetrical and polar. Remember the acronym SNAP? Symmetrical, nonpolar, asymmetrical, polar. But since you know the shapes, you have an advantage, and your advantage is, oh yeah, I know if I have a lone pair on that central atom, if I'm bent, if I'm trigonal pyramidal, I'm going to be polar. If I'm linear, if I am tetrahedral or trigonal planar, I have to check and see. I got to see if I am going to be polar or not. Now, just to go over a few properties of these different kinds of compounds. So ionic, we talked about this early on, and I wrote it here again. When you're ionic, you have high melting points, high boiling points. If I dissolve an ionic compound in water, it forms ions. The ions can move, it can conduct electricity. If I'm polar, when I'm polar, I tend to sort of have the ability to have a medium melting point. I can dissolve in water. And depending on the polar compound, if you are an acid, you can actually conduct electricity in water. If you are nonpolar, then you don't dissolve in water at all. You have very low melting points and boiling points, and you tend not to conduct electricity. And I'm going to come back to this again when we do something called intermolecular forces and discuss that with you. Okay, I'm going to stop now for this video. It was a short one. I just wanted to go back and sort of clean up the polarity idea. My next video that I'll show you will focus only on the orbitals and the bonding of the orbitals. All right, thanks so much.